Hello everyone, this is Adhish. I'm a grade 10 student from Mumbai. So today's problem is robot walk. The difficulty level of this problem is easy medium, and the only prerequisite you need to know to be able to solve this problem is dynamic programming. More specifically, you should know the subset sum to zero problem and how we can solve that using two-dimensional dynamic programming. So before I explain my solution for this problem, I encourage you to go to this URL and try to solve this problem on your own. And then I'll explain the problem statement and my solution. So in this problem, we are basically given a programmable robot and which can have the following three properties. The robot can only move forward in the direction which it faces, which is either horizontal or vertical. Each time after it moves, it can rotate by exactly 90 degrees. So either to the left 90 degrees or to the right 90 degrees, or basically clockwise or counterclockwise 90 degrees. And the robot is designed to turn exactly n times. This means that the robot has to move forward n plus 1 times. So basically we need to give it two n plus 1 values. The n values will represent the number of times it will turn, and n plus 1 values will represent the number of time it moves forward. So the actions are the following. It first moves north, so we can consider to move plus y in the positive direction. Then it basically moves a0 steps in the positive y direction. Then if it's left, it turns 90 degrees, so it basically moves in the negative x direction by a1 steps. Or if f1 is right, it turns 90 degrees and it basically moves right by a1 steps, or basically it moves to the delta x, or basically the change in x is plus a1. And similarly in the next step, it either turns left or right, so it basically again either moves a2 steps in the positive y direction or a2 steps in the negative y direction, and it repeats all of this up until the nth step. And now we need to test this robot, or basically chef needs to test this robot, and he needs the robot to return to its exact starting position. So basically in the end, the delta x and the delta y should be 0, or basically the x coordinate and the y coordinate of the robot should be 0. And to do this, he can do two kinds of operations. The first operation is change ai by some number x, and that takes x seconds, because each change in the AI values take 1 second. And he can change the direction of the robot in 0 seconds. So basically he can each time choose whether he wants the robot to move in the plus y or the plus or the negative y direction, if that is the orientation of the robot, or he can choose with 0 cost whether to move the robot in the negative x or the positive x direction. And we need to basically find the minimum number of the first type of operations which we should do to make the robot come back to its original position. And we need to answer this for t test cases. It's important to note the constraints that t is less than or equal to 50 and n and ai is less than or equal to 500. I'll mention this later as I explain the solution, why it's important. And if it's impossible to accomplish this task, we just need to print no. So let's look at the two examples. In the first example, the AI values are 11, 7, 11 and 7, and we can essentially ignore the directions because we know that the cost is 0 to change the directions. And now it's easy to see that there's a plus 11 in the positive y direction, then you can make it a plus 7 in the positive x direction. Then you can orient this, you can basically orient the robot so that it's moving 11 downwards in the y direction and 7 to the left, or 7 minus 7 in the x direction, and that's why we can just keep the same AI values and the cost is 0. For the second sample test case, we need to change the second AI value. We need to basically make the 9 to equal to 7 so that the 11 positive y and basically the 11 negative y will cancel each other, in this downward direction, and the positive 7 in the rightward direction or in the positive x direction will cancel with the negative 7 in the a negative x direction, and that's why 9 to 7 takes 2 operations, and that's why the cost is just 2. And those are our examples. So now that we have understood the problem statement, I'll now explain the key observations required to solve this problem. So the key observation is, first of all, as I was explaining the problem statement, I was inherently using this observation, and that is to consider the two components of the robot's position. There's an x component and a y component. And now let's analyze these n+1 moves which the robot makes. So the robot each time will move. So in the first move, his y direction is fixed. He needs to move in the plus y direction. And from the second move onwards, he can basically choose between plus x or minus x, then plus y or minus y. Then again, he can choose between, in the fourth move, he can choose between plus x or minus x, and all the way up till the n+1th move. Or basically, if you consider zero-based indexing, then 0 to n. And that's the first observation which I was inherently using. And now this pattern which I've written down below is actually very important, because we know that each time we can basically fix the direction. We can choose the robot to move in the plus y or minus y direction. Note this happens only after move 2 onwards or move 1 onwards. In move 0, the direction is fixed. After that, we can choose either to move in the plus x or minus x, or the plus y or the minus y. So we can do this with a cost 0. And notice that since the robot has to come back to the initial position, we need the delta x and the delta y to be both equal to 0. So that's why we basically need a sum to be 0. And this should remind you of the subset sum problem, which uses dynamic programming, and the actual DP solution for this is kind of similar. So we basically need to use this. We basically need to make the sum 0. And what we can basically change is the AI values. So we can change the length by which we are moving with the cost equal to the absolute value of the final length and the initial length, or that's basically the quantity by which, the absolute value by which we change the AI values. So we need to make the sum 0. And first, let's just try to approach a simpler version of this problem, which is just checking whether the answer is 0, or basically whether the sum is already 0. So is the sum already equal to 0 is what we'll be checking. And there may be various ways to do this, but I'll be presenting a dynamic programming approach to check whether the sum is 0. And that DP approach will actually lead us to generalizing that same DP approach, or basically using the same DP table to find out the final answer. So now I'll be presenting the DP approach to check whether we can assign directions without changing the lengths, so that the delta x and the delta y are both 0. Also, an important note before we go on to actually look at the DP approach, we should realize that we are dealing with two components, and that's why we'll be basically building this DP table and use that DP table for both of those components separately. So right now, basically the two components are actually very symmetric. So that's why let's just say that we are dealing with only one component, and we are trying to figure out whether the sum is 0 for one component. The second component will be handled in the exact same way. Actually, we can use a method which just takes one component and does the same for the other component, and I'll be explaining that in the code. But for now, let's say that we are given an array and we need to choose signs for each element in that array so that the sum of all the elements is 0. That's the problem which we are trying to solve. And that can be solved by using a 2D dpij. So dpij is true if it's possible to make the sum of the first I elements equal to j, and by choosing the signs of each element in the array for all the elements up to I. So for the first I elements, can we make them equal to j by choosing the signs appropriately? And note that there is no cost to choosing the signs. That's why it's just a true or false value. It's a Boolean DP. And to be able to solve this DP, we need to make the recurrence. So the recurrence will just be either we choose the ith element to be a plus array of I or a minus array of I. So if it's a plus array of I, then basically it's going to be dp of I and j minus, it's going to be dp of I minus 1, sorry, because we have I minus 1 elements left, and the sum of the I minus elements should be j minus array of I. So it's going to be this, or basically, because it's a true or false thing, so that's why it's going to be or dp I minus 1, and let's say we chose array of I to be the negative value, so that's why in this case it's just going to be j plus array of I. Now, although this dp recurrence is correct and the base cases can be found out simply, we can just set the base case to be dp 0 0 is true, all the other dp values are false for obvious reasons. And although this dp is correct, we actually need to optimize this dp a bit, so I'll be mentioning the two optimizations immediately. The first optimization is that j minus array of I can actually become negative, and we don't want to handle negative indices in our dp table. That's why it's important to observe that if we just negate the whole thing, so basically we want the sum to be j minus array of I. J minus array of I is negative, and let's say we are able to choose signs so that we get a sum of j minus array of I. Then if we just negate each of those signs, what you'll realize is that we actually can get a sum of array of I minus j. So if we just negate all of those signs, we can just get a sum of array of I minus j, and that's why in the first case over here we'll just do absolute value of j minus array of I, and not the basically this thing, because this thing can be negative, and if it's negative, I just told you the argument for why the absolute value basically works. So that's the first observation, and the second observation is related to the second part of this basically the expression. So the first part of the expression can be optimized in this manner, and the second part of this expression can be optimized by using the fact that we only need to calculate this value for those elements. So basically j should belong to 0 comma the sum of elements so far, and that's basically just the sum of all array of x for x going from 1 to I. The reason why this is true is because j plus array of I will only reach those elements which are basically bounded by this sum condition. So the maximum value of this j thing can be only j plus array of I, and that maximum term can only be this whole sum. And this optimization is important because when we are basically computing dpij, we'll compute dpij only for those elements which are equal to the sum of x going from 1 to I array of x. And in this way we'll actually optimize the time complexity of our dp. So now that brings us to the time complexity. So the time complexity of the dp is actually n into the sum of array of I. Like, that's the time complexity if we don't do any optimizations. So if we don't perform the second optimization, then the time complexity is actually very, very high. It's going to be 500 cubed, because 500 into the sum of all elements, and the sum of all elements is at most 500 square. So 500 cube obviously won't work in 3 seconds, considering that there can be 50 test cases. So that's why we actually need to do this optimization, which is computing the dp values only for like these bounded elements. And there's actually a third optimization which relates closely to this time complexity. So we should actually extend this logic of computing the dp I comma j only for those elements which are equal to the sum of all the array of I by sorting the array. Now, why do I sort the array? That's because let's say that the array is sorted, then you should realize that at each moment the sum of the elements is minimized. Now what that means is that if you consider the elements in sorted order, then the minimum value of this term, the minimum value of this sum will be achieved only when the array is in sorted order, in increasing sorted order. If the array is in some other sorted order, or basically is not in a sorted order, then you'll realize that we actually need to compute dpij for more values of j. So that's an intuitive way in which you can understand why we should sort this array. And actually these two optimizations, these two time optimizations, so these two optimizations are actually to pass the time limit, and this is actually to pass the memory limit, otherwise we have negative indices. So this memory limit optimization is obviously necessary, otherwise we won't pass any test cases. And this time optimization is necessary because I actually submitted a code without one of the optimizations. So I basically submitted 3 codes. One was with this optimization but without this optimization. The second one was with the third optimization but without the second optimization. And the final one was with both these optimizations. Only the code with both these optimizations passed. So the time limit is actually very strict, and that's why both these optimizations are required to get AC. So anyways, going back to the problem statement, what we have realized is that we can compute the Boolean value is the answer 0. Now, how does that help us? At first glance, it may not seem to help us that much, but if you look more closely, then you'll realize that the minimum value of j, the min j, such that dpij is true is the answer. Like that's it. So if dp, so basically if dp of the size of array, comma, so basically this is the size of array, so this is like, let's say n is the size of array, so dpnj is 1 is the answer, because so in the first case we know that the sum is 0 only if dpn0 is 1. So in that case the answer is 0. And if you notice the case when dpn1 is 1, in that case we know that we can get a sum of 1, and we'll basically change the array so that the sum becomes 0 in exactly one operation. Similarly, if we choose a higher value of j such that dpnj is 1 or basically is true, then we can basically convert the array so that the sum becomes 0 using exactly j operations. So that's the intuitive reasoning. And for a formal proof, you can just check the written editorial. I won't be explaining the formal proof because it should actually be very intuitive to understand why, if we know that we can get a sum of j by assigning the signs, then we can also make the sum of the whole array equal to 0 in exactly j operation. So it's quite intuitive to understand, and for a formal proof you can check the editorial. So to summarize, we have basically figured out that the final answer for one of the two components is basically given by dp and j, and we'll consider the sum, we'll basically consider the x component and the y component, and we'll add up those two costs. So that's the final answer. So if we basically define a method cost of a component and basically of a cost for a component, then the final answer is just cost for the x component and plus the cost for the y component. And now I'll be explaining the specific implementation details with the help of my code. In case you didn't get the solution fully, you should be able to understand it with my code. So in the code, I have a global Boolean array dp, which basically stores whether or not, so basically dp n comma j stores whether or not it's possible to get a sum of j using the first n elements. Now I used a Boolean dp as I mentioned, with all values initially false and only 2 parameters. 2 parameters is required because to pass the memory limit, because 500 cube does not work. And if you notice, then each value of dpij is dependent only on I minus 1. So that's why I'll be basically using I percentage 2 to access the ith element. So that's why that's an additional optimization which you need. Now I have a cost function. So for now, let's assume it's a black box, and then I'll explain the DP used in the cost function. So in the main code, I take in the value of t, which is the number of test cases. For each test case, I basically read in the input, and in the input, I basically create the x component. So vector b refers to the x component, and vector b actually refers to the y component, and vector c actually refers to the x component. So I'll basically add the corresponding value to the corresponding component, and in the end I basically print cost of b plus cost of c. So cost of some array basically tells us the cost to make the sum of all elements in the array, so in array A, equal to 0 by assigning the appropriate signs and by basically changing some elements. So that's our cost function, which I'll explain just now. An additional note is that if n is less than 3, the answer is no, and you should try to prove this by yourself. I won't be explaining too much because this should be clear to you. And now I'll be explaining the DP solution. So in the DP, I initialize DP00 to be 1. Then I basically compute the remaining DP values. As I mentioned, I'll be computing DPij for all j going from 0 to some. DPij is basically going to be equal to DP I minus 1 of j plus a of I minus 1 or DP of I minus 1 and j minus a of I. One thing to note in the solution is that I use I minus 1 because array A uses 0 based indexing. So sorry for making this a bit confusing in the code. Like a of I minus 1 is there because the vector A is 0 based indexing. You could actually use a of I, like this would be the actual technically correct thing, but practically we need to use I minus 1 because it's 0 based indexing. So this is our occurrence, and for the final answer, which I have to compute in this loop itself, otherwise the time limit is very strict, so you need to update the final returning value over here only. So the returning value will basically be a minimum of itself and j when dpij is true. So when dpij is true and we are at the last element. So in that case, we basically update the return value and we just print the return value. Notice that I'm using dp repeatedly. That's why I need to update them. I need to re-update them to all zeros, and in the end I return. And actually, if you noticed, I don't even need this condition. I basically can just check if the cost of b plus cost of c is equal to or greater than 10 to the power of 9, then we print no. Otherwise we print this cost. Either ways your code should work, so you should actually try to implement it the other way, which is basically just checking if the sum of the costs is 10 to the power of 9 or more. And now I'll just submit this code to see that it gets accepted. So as you could see, my code got accepted and it took a lot of time. So this problem was very strict in the time limit. But anyways, I hope you understood my solution and you liked the problem and my solution for this problem. If you had any doubts, do leave them in the comment down below. If you liked this video, don't forget to give it a thumbs up.